Relations, the second time around. We will start our discussion of relations and their properties by reviewing the definition of a relation. Subsets of A cross A are called relations on A. An example, if A is equal to the set 1, 2, and 3, then A cross A will equal to, we'll start with an element, the first element of set A, and we'll combine it with 1, 2, and 3. So we'll have 1 combined with 1, 1 combined with 2, and 1 combined with 3. Then we'll take the second element 2 and combine it with 1, 2, and 3. So we'll have 2, 1, 2, 2, and 2, 3. And then last, we'll take the last element of A and combine it with each of the elements of A. 3, 1, 3, 2, and 3, 3. So there should be a comma, and this should not be there. So this is A cross A. Now our relation is any subset of A cross A. So I could say, I could define the relation 1, 2, and 2, 2. And again, this is just arbitrary. I could choose any of the elements and say it's a relation. And just some notation, we say 1, 2 is an element of our relation, or we can say 1 is related to 2. 2, 2 is also an element of our relation, and 2 is related to 2. So I just kind of neatened that up with some typing. I can also define my relation in this fashion, where I say R is a relation on Z defined by A is related to B if A is less than or equal to B. In this case, since our relation is on the integers, 3 would be related to 4, since 3 is less than 4. So that would be one example. So there are properties that relations may or may not exhibit. The first property we will discuss is the reflexive property, which is for all elements of A, then X is related to itself. The symmetric property says if X is related to Y, then Y is related to X. The transitive property says if X is related to Y and Y is related to Z, then X is related to Z. There are a couple of definitions. A relation is called anti-symmetric if for all A and B in the set A is related to B and B is related to A implies that A is equal to B. And one more definition, a relation is called a partial ordering if the relation is reflexive, anti-symmetric, and transitive. Okay, so there is one more definition. A relation on A is called an equivalence relation if the relation is reflexive, symmetric, and transitive. So we'll do some examples. So we'll start by trying to see if our relation is reflexive. And I'll put a question mark because we're trying to determine whether or not it's reflexive. If it's reflexive, looking at our definition, that means for all X in our set, everything must be related to itself. So if reflexive, for all X, in this case we're looking at our set of integers, is X related to itself? And I'll put a question mark again. We're trying to verify, determine if this is true or not. And then I'm going to replace this general relation with our particular relation here. So I'll say for all X in Z, is X related to itself? And in this case, it means less than or equal to itself. And the answer is yes. so it is reflexive. Next, we'll consider if this relation is symmetric. And again, I'll put a question mark because we're trying to determine whether or not it is symmetric. To see if it's symmetric, we want to say x related to y implies y related to x. So just to remind myself, I'll write that down. X is related to y implies y related to x. And I'll put a question mark. Again, we don't know. We're trying to verify. So I'm going to replace this general relation with our particular relation, a is less than b. So I'm going to say x less than or equal to y. Does that imply that y is less than or equal to x? And again, it's a question mark. We're trying to verify it. And in general, for integers, no, it is not true. So it is not symmetric. So there's no symmetry there. Just because x is less than y, it doesn't mean that y is less than x. Last, we'll consider whether this relation is transitive. Oh, we could probably also look at anti-symmetric, so almost last. So if it's transitive, x is related to y and y is related to z implies x is related to z. And I'm going to put a question mark. And I'm just going to remind myself what it means to be transitive. And y is related to z implies x is related to z. A question mark because we're going to verify it for this relation, replacing the general r with our particular relation, x less than or equal to y and y is less than or equal to z. Does that imply x is less than or equal to z? Well, for integers, this is true. So yes, this is transitive. And now last, we'll look at anti-symmetric. And again with the question mark, we're trying to verify. If it's anti-symmetric for all A and B in the set A related to B, and B related to A implies A equals B. So again, I'm going to start replacing my general relation and my A with my particulars here. And I'm going to put a question mark. So for all x and y that are integers, if x is less than or equal to y and y is less than or equal to x, does that imply that x equals y? And for integers, yes, that is true. So it is anti-symmetric. Just a quick note, in this example, we have something that is not symmetric, but it is anti-symmetric. It is not the case that anti-symmetric means the opposite of symmetric. So there are relations that are both symmetric and anti-symmetric, or relations that are both not symmetric and not anti-symmetric. Our next example, we'll look on a relation on Z. A is related to B if A is equal to B. So first we'll consider if this relation is reflexive. Again, we'll consider it, so we'll put a question mark. And we want to know if it's reflexive if for all x in A, if x is related to itself. So we're going to replace these generic r's and generic sets with our particulars. So in other words, for all integers, is it true that x is equal to itself? And the answer is yes. So this relation is reflexive. Next, we'll consider if this relation is symmetric. And just to remind ourselves, symmetric means if x is related to y, then y is related to x. And we're going to ask, is this true of this relation? So we'll plug in our particulars. If x is related to y, does that imply y is equal to x? And for integers, yes, that is true. So this relation is symmetric. Next, we'll look to see if it's transitive. if x is related to y and y is related to z, is it true that x is related to z? So replacing our r's with their actual relation, if x is equal to y and y is equal to z, does that imply x is equal to z? And that is also true. So this is a transitive relation. Last is anti-symmetric. For all A and B in A is related to B and B is related to A implies A equals B. Replacing R with our relation for all x and y and the integers, if x, and what are we doing, equals y and y equals x, does that imply x equals y? And that is yes. So this is anti-symmetric. Also note, since this relation is reflexive, symmetric, and transitive, it is also an equivalence relation. It is also reflexive, anti-symmetric, and transitive. It's also a partial ordering. But the stronger thing to say is that this is an equivalence relation, and it's also a partial ordering. Our last example has a little bit of a different notation. It says R is a subset of Z positive cross Z positive, and A is related to B if A divides B. So just looking at this notation, it's actually quite consistent. It's just a different way of saying relation and of expressing our relation. Remember, Z cross Z, or Z positive cross Z positive, are all ordered pairs with positive x and y's. And remember, we could say if A is related to B, we could have expressed that as saying AB is an element of our relation. So that's just highlighting here, taking this notation and saying that R is a subset of our Z positive cross Z positive. You do want to make sure you understand this notation because there are relations on Z cross Z. In this case, R is not a relation on Z cross Z. R is a relation on Z positive, and it's a subset of Z positive cross Z positive. But we'll continue with our example and discussing whether or not first this relation is reflexive. So is it true for all x in our set that x is related to itself? In other words, for all x in Z, is it true that x divides itself? And the answer is yes. So this relation is reflexive. Next, we'll consider if this relation is symmetric. In other words, x is related to y. Does that imply y is related to x? Replacing our with our relation, our particular relation, if x divides y, does that imply that y divides x? And the answer is no. So it is not symmetric. Is it transitive? X is related to y and y is related to z implies x is related to z. Substituting our relation, our particular relation, x divides y and y divides z, does that imply x divides z? The answer is yes. Oops. The answer is yes, and this is from Theorem 4.3 in Chapter 4, when we talked about integer division. So it is transitive. So last we'll consider whether or not it is anti-symmetric. For all A and B in set A is related to B, and B is related to A, implies A equals B. There's a question mark there. I wanted to write one, but I ran out of space. So for all X and Y in the positive integers, if X divides Y and Y divides X, does that imply X equals Y? And this is true for the positive integers. So it is anti-symmetric. So here we have an example of something a relation that is reflexive, transitive, and anti-symmetric. So that makes this a partial ordering. It is not an equivalence relation since it's not symmetric. So now we have discussed relations and their properties, in particular reflexive, symmetric, transitive, and anti-symmetric properties. So we're ready to talk about equivalence relations. Remember, those are the ones that are reflexive, symmetric, and transitive, and the partitions that they produce. But first, I am going to tell you a joke, which I know this is a very strange transition, but in Chapter 2, I told you a math joke, and that fit in very well with the topic. So this one doesn't fit in so well with the topic, but it's towards the end of the class, so I have to fit it in, and it's my absolutely best joke. So here it is. So I'm going to set it at Rice University. That's where I was an undergraduate. So at Rice University, there's this professor. We're going to call him Dr. Philman because that's the person, even though he didn't go to Rice, that's the person who told me this joke. So Dr. Philman, he's there. He's a professor. He spent all his life, studying, learning intellectual things, intellectual pursuits, pursuing wisdom, knowledge. One day a genie appears to him and says he will grant him one of 3 wishes. So he has to choose one, either absolute beauty, absolute wisdom, or absolute wealth. So naturally, Dr. Philman, being a professor, chooses absolute wisdom. And poof, he's absolutely wise. So news of this travels throughout the whole campus. Everyone's heard of this, the absolute wisdom. And so some students come to talk to Dr. Philman, and they say, please, professor, share some of your wisdom with us. And so Dr. Philman thinks for a minute, and he says, I should have taken the money. There it is. That was my best joke. And remember, he's absolutely wise. So that's the wisdom I had to share with you. And now we can go on and talk about equivalence relations and their partitions that are reflexive, symmetric, and transitive. We have a definition. Given a set A and an index set I, let A sub I not equal to the null set and a subset of A for each element little I, that's the index set, the particular I in the index set I, then A sub I is a partition of A if A is equal to the union of all the A sub i's, and each A sub I are disjoint. So their intersection is null as long as we're talking about different A sub i's. Every subset A sub I is called the cell of the partition. And essentially what a partition does, it divides A into smaller subsets A sub I that are mutually disjoint. An example, let's say that we have an example A that's equal to 1, 2, 3, 4, 5, and 6. So I could say that I could start and say my A sub 1, and I could put anything in A sub 1. I might just start with my first 2 numbers, 2. So since A sub I, all the A sub i's need to, when you union them, need to equal to A, so I need to have another partition. So maybe I'll throw in 6 in there. And again, they need to be disjoint. So these 2 are disjoint, so I'm doing pretty well. But again, if I union these 2, I still have members I need to throw in. If I just want to have one more cell, that would mean I would need numbers 3, 4, and 5. And again, this is considered a partition because the union of A1, A2, and A3 would equal to A, and A1 and A2 are disjoint, A1 and A3 are disjoint, and A2 and A3 are disjoint. So let R be an equivalence relation on A, and let X be an element of A. The equivalence class of X, denoted with the brackets, is defined by every Y such that Y is related to X. We'll do an example of this, but first let's go ahead and look at the theorem. So if R is an equivalence relation on A and X and Y are elements of A, then 1, X belongs into the partition, the cell that contains X. And if X is related to Y, well, X is related to Y if X and Y are in the same cell. And X and Y, if the cells are equal, either the cells are equal or they are disjoint. So the effect of this theorem is essentially this. An equivalence relation forms a partition on A. That is, an equivalence relation can be used to divide A into smaller, mutually disjoint subsets. So we'll look at a last example to bring all these ideas together. So we have a set A, which is equal to, it's the set A is a cross product. So A is equal to the set 1, 2, 3, 4, 5, 6 cross 1, 2, 3, 4, 5, 6. To say that A is a cross product means that we have to look and see what A looks like. That A, if I write out what A is, it's essentially this cross product, 3, 4, 5, 6. So essentially I have to take every element of A, and here I've started with the element 1, and then write it, pair it up with each of these elements in my second set. So here I have 1 paired up with each of the elements in my second set. Now I'm going to take 2 and pair it up with the elements 1, 2, 3, 4, 5, 6. I'm going to continue and I'm going to take 3 and pair it up with each of the elements 1, 2, 3, 4, 5, 6. And I'll continue with 4, 5, and 6, pairing it up with 1, 2, 3, 4, 5, 6. Okay, so here is what my cross product looks like. So here's my cross product. And that is what A is equal to. So we're going to talk about a relation on A. So if we are talking about a relation on A, it's going to relate elements of A with other elements of A. Just a quick note, to compare this to an earlier example, I said I had a relation R, which is a subset of Z positive, cross Z positive. In this example, R was a relation on Z positive, on Z plus. So in other words, we took elements of Z positive, maybe 1, and we'd say it was related to another positive integer, maybe 2, and we would say 1 is related to 2, so 1, 2 was an element of the relation. So that is what this notation was saying, that R was a subset of Z positive cross Z positive. In other words, it was a subset. The elements of R were basically ordered pairs. In this example here that we are doing, our set A is a set of ordered pairs. It's quite different here where our set is a positive integer. But here our set A is ordered pairs, a set of ordered pairs, and we're going to relate ordered pairs to other ordered pairs. In particular, our relation is the ordered pair x1, y1 is related to the ordered pair x2, y2 if x1 plus y1 is equal to x2 plus y2. So first we can verify that this relation is reflexive. I was going to write symmetric, but I wanted to say reflexive. So the first thing we ask is, for all xy pairs, is it true that xy is related to itself? That's our question. So in other words, substituting our relation, the definition of our relation, is it true for every xy that x plus y is equal to x plus y? And the answer is yes. So this is a reflexive relation. We can verify this relation is symmetric. So if xy is related to x2, y2, does that imply that x2, y2 is related to x1, oh, I just said xy, I didn't put any subscript before, that's a question. Plugging in our particular relation, so if we said x plus y is equal to x2 plus y2, does that imply x2 plus y2 is equal to x plus y? And the answer is yes. So this is a symmetric relation. And I need some space, so I'm going to shrink this over. And we'll ask last, is it transitive? Because I wanted to verify this is a equivalence relation. So if x1, y1 is related to x2, y2, and x2, y2, this is a 2 and that's a 2, is related to x3, y3, does that imply x1, y1 is related to x3, y3? And that's our question. In other words, if x1 plus y1 equals x2 plus y2 and x2 plus y2 is equal to x3 plus y3, does that imply x1 plus y1 equals x3 plus y3? And the answer is yes. So this is transitive, and this is an equivalence relation. So I wanted to look a little more at what the partitions look like. So let's take, for example, the cell 1, 3. So the things that are equivalent or in the same cell as 1, 3 are the things that sum to 4, are the ordered pairs that sum to 4. Remember, you just want to look at your definition of the equivalence. So they're equivalent or in the same class if they sum to the same, the ordered pairs sum to the same number. So in this case, the equivalence class for 1, 3 is 1, 3, 3, 1, and 2, 2. Because these are the ordered pairs that sum to 4. Looking at another equivalence class, the equivalence class of 2, 4. So the things that are equivalent to 2, 4 are the ordered pairs that add to 2 plus 4, 6. So that's going to be the pairs 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1. And in fact, this matrix here is drawn in such a way to find the equivalence class quickly. They're basically everything on the same diagonal. So here's the equivalence class that sums to 2. This is the equivalence class that sums to 3. The equivalence class that sums to 4. This is 5, 6, 7, 8, 9, 10, 11, and 12. So I'm going to shrink this to give me a little more space so that I can answer the question, what is the partition? That should be partition of A induced by R. So I can start with the equivalence class represented by 1, 1. That's the class that sums to 2. Next, I can look at the class that sums to 3, and I'll just choose one representative element, 2, 1. So I could have written 1, 2 instead. The next one is the equivalence class that sums to 4, so I'll choose the representative element 3, 1. I'll include the equivalence class represented by 4, 1. And then I have the equivalence class represented by 5, 1. The equivalence class represented by 6, 1. So I'm over here in my matrix, so now I need to go to 6, 2. Oops. Union. The equivalence class represented by 6, 2. 6, 3. 6, 4. 6, 5. And 6, 6. So this is my partition. And again, if you want to know what the other elements in this cell, in the 2, 1 cell, it's here in this matrix. And here's all the elements in the cell that's equivalent to 6, 1. So that concludes this video. We discussed relations and their properties, in particular the reflexive, symmetric, transitive, and anti-symmetric properties of relations. And then we defined equivalent relations as those that are reflexive, symmetric, and transitive. And we discussed equivalence relations and their partitions. In our next video, we will discuss finite state machine minimization. Thank you for listening. I'll see you in class.